Right, well, good afternoon, everybody. Oh, I like it. My name's Roy Lowry. I'm an associate professor here of physical chemistry, which sounds terribly grand. I also have another job. I get to set up very large-scale public firework displays. So I thought this afternoon I'd teach you a little bit of the science of fireworks. So for the next 60 minutes or so, this theatre space is actually going to turn into a science laboratory. Now, I hope you've worked out that whenever you walk into a science lab, there's usually big notices about, safety first, you must be wearing the right protective gear and this sort of stuff. So the first thing I'm going to do is change these rather modern specs for something a little bit older, but these are proper safety specs. You're probably thinking, if I'm a scientist, I should be wearing a white coat. I'm not going to be wearing a white coat because, given the nature of the experiments I'm doing, that would not be a very sensible thing to do, have long, baggy sleeves, because I'm going to be playing with fire quite a lot. To give you an idea, the name of the talk is Pyromania. One of the things about science is we do like coming up with clever names, though we're not very good at it sometimes. And we tend to use either Latin or Greek. This is actually based on the Greek. Pyro comes from the Greek meaning fire. Mania is also from a Greek root from which we get the English word maniac. So actually what that tells you is there's a maniac at the front who's going to be playing around with fire. Now when we start talking about fireworks, wouldn't it be great to actually start off a lecture demonstration with a pile of gunpowder? I mean, that's what really powers fireworks, wouldn't it? But of course, gunpowder, it's dangerous stuff. I mean, you can't just let anybody have gunpowder. It turns out that if you have the relevant PhD and degrees in chemistry, people think you're sensible. How wrong can they be? So I've got a nice canister of gunpowder here. And we're going to start off with a little pile of gunpowder. Actually, no, we're not, because you lot are quite a far way away. So we're going to start off with a big pile of gunpowder. A bit more, maybe. Yeah, a bit more. There we go. We'll put the rest of it away because we really don't want it joining in. There we go. And then I need a really nice high-tech piece of equipment to set my gunpowder off. So we'll just... just. There we go. So we can have the lights down a little, please. That's only taking the lights down. The ooh should come when the gunpowder goes off, if you don't mind. So, that young man in the front row is not looking too happy. Just remember, I'm closer than you are. However, I've got a standing start. All right? Now, there were a couple of people sat there like this. Maybe one eye open. Expecting it to go bang. Gunpowder doesn't go bang. Gunpowder, well, you can make it go bang, but that's a branch of science called physics, and I'm a chemist, so I don't go there. Gunpowder has been around for a long time. If you want to see an argument, ask two historians how long gunpowder has been around, and they'll have an argument because they'll disagree with one another. We think at least, 2.5, maybe 3,000 years. And it's very, very basic chemistry, you think, but actually we still don't know all the ins and outs of the chemistry of how gunpowder works. It's a very simple mixture. It's based upon charcoal as a fuel. Now, I don't know about you, but on those very rare days, especially in Plymouth, when it's suitable for a barbecue, what doesn't happen is you get the barbecue out, you put all the charcoal on it, you put the griddle on the top, a few chicken wings, maybe the odd bit of vegetables, and then you don't go, everybody ready? Here we go. Woof, chicken's ready. It doesn't work like that. But that was charcoal, and it burnt an awful lot faster than the charcoal you see in a barbecue. Now, there's two reasons for that. First of all, whoever it was that invented gunpowder realised, first of all, that when you've got a lump of charcoal, the only place that it burns is on the outside. Because there you've got the fuel, the charcoal, and you've got the air from the oxygen. And it's those two reacting together that give you the fire. In the middle, you've got charcoal next to charcoal. Boring. It's only on the outside, but it actually burns. So by grinding up the charcoal until it was very small, you end up with lots of outside and very little middle. And so the charcoal burns much more quickly. Okay, step number one. Still not going to go that fast, though. The second idea was brilliant. I don't know who came up with it, but what they've done is they've put a solid compound into the pores of the charcoal, which is basically semi-burnt wood, so it's got all the pores from the tree in it. And that, when it gets hot, releases oxygen. So you've got that in there. So some lunatic like me turns up with a little source of heat. The charcoal starts to burn. The compound gives off more oxygen, which means now that the charcoal can burn more quickly because it's got more oxygen. Because therefore it produces more heat, which means the other one produces more oxygen, which means the charcoal burns more quickly, which burns more, as you saw. That compound we now call potassium nitrate. We used to call it saltpeter. It's gone under a whole variety of names. And they needed a source of this. And one of the theories the historians have come up with for the source of saltpeter is that the sort of time in history we're talking about, people used to live in villages or communes of about 300 people. And everybody would use the same loo. Well, I say loo. It's a hole in the ground. The deluxe version has a plank over the top to stop you falling in. So everybody's, I'm a university professor, I have to use proper words here, stuff ends up in this hole in the ground. And it gets warm and the water starts evaporating and all the salts from the urine start to crystallize out. Because at the moment, there's about 120 sources of this potassium nitrate in this room because your kidneys are excreting it. And you'll be making a donation to the local sewage company sometime later, not now, please. Thank you. So these crystals would appear on the walls of this deep pit. And the theory goes that maybe once a year they'd get a lad of about 7 or 8, tie a rope around him underneath his armpits, and lower him into 300 people's stinking year-old wee. And his job was to swim to the side wall to scrape off the crystals of potassium nitrate. And they would then be taken away, purified, and used to make gunpowder. And that's what makes the fuel, the charcoal, burn so much more quickly. Now, I have to be very careful because in this country, if I tell you how to make gunpowder, I break the law. But it's okay because actually there's 3 constituents of gunpowder. I've only told you 2. So providing I don't tell you the other one is sulfur, we're fine. So, gunpowder, still the basis of fireworks. A, because it's pretty cheap. B, because it's very good as a propellant. It doesn't suddenly blow everything apart. It propels things well. You get that sort of, you saw how the gunpowder sort of burns and then dies away again. And that's excellent as a rocket fuel. So, you know, the rockets that you use for, in little garden displays or something, basically a cardboard tube, ram it full of gunpowder, little twist of blue paper on the end. No idea why it's always blue, but it usually is. Stick to hold it up in the right way. Actually, if that's all a rocket was, it'd be very boring. You'd invite everybody around to your place for a firework display and get the barbecue going, which would take ages. And you get the rockets out and you go, right, everybody ready? Here we go. And everybody go, great. It's a cardboard tube in the air. That's really exciting. Can we go home now? You need it to do something when it's up there. Well, guess what? We can do that using chemistry. Now, what I've got in here is something that burns, but also I've put in here something that when it burns, it produces different coloured lights. So, for instance, here, I'm using the element strontium to give us a nice, strong, bright red flame, and this is how we make Roman candles, Catherine wheels. It's also the chemistry behind distress flares. Whenever you see a red light in the sky produced by something like this, it's going to be the element strontium. So, we can do red. We can do yellow. This is a very expensive chemical. This is sodium chloride, common table salt that gives you that yellow flame. So if you've used a gas cooker and the vegetables have boiled over, that's why the flame goes bright yellow. We can do red, we can do yellow. Oh, yeah. Hey, funny that, isn't it? I've been doing this for quite a long time. And it always used to be that when I did this, everybody would go, oh, red, yellow, yeah. And by the time I got to green, it was like, and then all of a sudden, literally over the space of a month or so, everybody decided green flames were really cool, and I couldn't work out why. Fortunately, my wife told me why. Because this was the time of the first Harry Potter film. And there were a lot of green flames in the first couple of Harry Potter films. And they were all produced like this. This is the element copper, which gives this the flame a lovely green colour. And so that's how we make our green fireworks. We've done red, yellow, green. This one tends to be used for fireworks for weddings, because apparently this lovely soft pink is a very romantic colour. I've never understood that, really. Hello, I love you, I want to spend my life with you. Stand there while I set light to you. No, it doesn't work. There were several girl bands doing tours quite a few years ago. Spice Girls, Girls Aloud, they use quite a lot of this in their stage shows. So we're done, red, yellow, green, pink. Just to prove I can get to the end of the spectrum, this one is purple. It's not very bright. It's not very efficient at turning the heat energy into the light, but it does also show that this is not just the chemistry of fireworks, it's also the chemistry of the flamethrower. So everybody pay attention, because if you don't, especially if you're sitting on the front row. So, we can do all these different colours, but if you want to make really bright lights in the sky for fireworks, you need this material. This is magnesium. Magnesium is a metal. Most people think metals don't burn, and quite a lot of people have seen magnesium burn. I'm still going to do it, though, because like the thing on the screen says, I'm a pyromaniac. I'll set light to anything, given half a chance. But most metals do actually burn if you get the temperature up high enough. So, oh, that's quite a long piece of magnesium. Oh, that's quite good. So, this gets quite hot, so I don't think I'll hold it with my fingers. And it also needs a very high temperature to get it going. So at this point, that little flame isn't going to do it. So in comes the blowtorch. And you can see it burns with a bright white light. In fact, if you're silly enough to do what I've just done, which is look at it directly, you've now got a yellow streak down anything you look at, because the human eye can't quite cope with that amount of light all at once. It's okay, your retina will slowly come back to normal over the next couple of seconds or so. That's all right, but it's a bit slow. Yeah, I mean, you set light to one end and it sort of slowly crawls its way up. And the reason it's slow is because, well, I've measured the thickness of that piece of magnesium, and it's 1/10 of a millimetre. Now, that sounds very thin, but the atoms that make up everything we see, and quite a lot of the things we don't see, are so small that there's layer upon layer upon layer upon layer, and if I count them out at that sort of speed, it will take me over 100 years to count out all the layers of atoms that you could squeeze into 1/10 of a millimetre. I know this because I am so sad, I sat down with a calculator and worked it out. It's 100 years without stops for meals, going to the loo, sleep, or anything. Because there's a huge number of layers of these atoms. And it's only the outside layer that actually can react with the oxygen in the air. So the next layer has to wait until the first layer burns away, and then the next layer can burn away, and then the next layer can burn away, and the one in the middle is getting very bored because there's nothing to do. Mind you, if we can take charcoal and speed it up that much, could you imagine what we could do with magnesium? The magnesium version of gunpowder would would go pretty quick. So I thought I'd give it a try. And I started phoning specialist chemical suppliers saying, can I have very, very fine magnesium powder? Because that's what I would need. Several of them just said, no, sorry, don't do it, and put the phone down quite quickly. It was a little while later that one of them explained to me that actually the production of that material does happen, but they weren't going to sell me any because the only people allowed to buy it are people who supply armaments to the army. So I'm probably on somebody's list somewhere for trying to get hold of very fine magnesium powder. But if I could have got hold of it, I would just mix it with something else that when it gets hot produces oxygen, and we'd have the magnesium version of gunpowder, which would have been fabulous. And then I realized I could get hold of the mixture. This is a pot of the mixture of magnesium powder and a little something else. When you see a UN hazard warning diamond, which you might do on the news sometimes, it always has a number. And that number is in two parts. The first number, a little dot, and then a second number. The first number tells you the sort of hazard. In this case, it's number 1, can explode. The number after the decimal point tells you how bad the situation could be. 1.4 you will see on a box of garden fireworks that you can buy from a supermarket and set off in your own back garden. 1.3, well, that's half a kilo of gunpowder like I had earlier. 1.2, I will translate the rather technical English language into something easier. Seriously dodgy. 1.1 is as bad as it gets. This is 1.1. Thanks to knowing a graduate who works in a certain company, I'm not even allowed to tell you where their manufacturing facility is. I had to drive to the manufacturing facility and pick this up myself. I'm actually the only person in the UK that has this powder at the moment in sort of loose form. Oh, that's quite a lot. You're not scaredy cats in the front row, are you? Great. So, let's see what happens when we set off a pile of magnesium mixed with a little something that's got oxygen in it. I should warn you, this is one of the fastest chemical reactions known to humankind. If you blink, you will miss it. Here we go. And if you look at it when it goes off, you have a very large yellow something or other hanging in the air in front of you, and you can't really see what's going on. Have you seen that experiment before? Oh, yes, you have. None of you have been to the pantomime. Oh, what sad lives you lead. This is the chemistry behind Aladdin. If you go to the panto, Aladdin gets locked in a cave, fine, gets to the point where Aladdin rubs the lamp and a genie is supposed to appear. Now, I know I'm in a theatre and I'm about to tell you a theatre secret, but it's about time you knew the genie's an actor. It's not a real genie, okay? So there's Aladdin standing probably centre stage with the lamp, and you will always hear these words really clearly throughout the entire auditorium. Oh, I think I will give the lamp a rub. And actually it's not because the actor is practicing projecting the voice. It's actually code. Because backstage is the pyrotechnician. Now the pyrotechnician turned up before the audience, put a little box like that right on the front of the stage, and put a little device in it which contains the powder that I had. Now, it would look a bit silly if in the middle of a play, a member of the stage crew appeared with a blowtorch. It would give the game away. So we put something in there that means we can start the reaction remotely. It's a bit like a match, only it uses electricity. Now, I told you scientists are clever at coming up with terminology. This is called an electric match. That goes in there, the wires go off to the side, and they're wired into, it's always a black box with one control on it. A big, fat, red, maybe not juicy, button with one word next to it, the word fire. So when Aladdin stands there and says, I think I will give the lamp a rub, it's actually code, and it stands for, hey, pyrotechnician, it's playtime. And the pyrotechnician goes, and as he rubs the lamp, bang! The front row of the audience does exactly what it did about 60 seconds ago. Wow, that's bright. Wow, can't see a thing. Complete wipeout. Oh, hang on, smoke. My vision's coming back. There's a genie. How did they do that? And it's all quite literally, well, no mirrors, but smoke. Yeah. The other place you might well have seen it is if you've gone to a rock concert. I can absolutely guarantee at some point or another, several of these boxes were along the front of usually the drum riser, quite possibly in front of the lead guitarist, and at the end of what we call the first half closer, just before the interval, when you all go out to the bar or buy the T-shirts, the pyrotechnician will be, again, out in the wings, and just as the drummer goes round the drums and lays into the cymbal, bang, the front of the drum riser lights up bright white, and everybody goes, that was amazing, I must buy the T-shirt. Yeah. And in fact, for a couple of years, that was my job. I used to blow up lead guitarists on a regular basis, and it's a very satisfying job to do. It's time to cut the waffle, really. It's time for me to do the most dangerous experiment I'm going to do for you this afternoon. The reason it's dangerous is because I'm never really quite sure how well it's going to go. On a scale of 0 to 10, sometimes I get a 0, and it just ends up like a fire extinguisher. It's not clear. Most of the time I get a 7 or an 8, and that's quite nice. Occasionally I get a 10. Once or twice I've had a 13, and that scared me quite a lot. I'm sure you can understand that since I'm an academic at a university and I work in a chemistry department, I can get hold of some pretty dangerous stuff. In this case, I'm talking about something that's very much almost a British institution. It's called Angel Delight. This is mixed with milk to make a pudding. Very strange stuff. Now, just to prove that this is perfectly ordinary Angel Delight, I've not opened the packet because some people think I'm some sort of chemical conjurer, but I'm not. So I'm going to tear the top off this. I'm going to try and set light to it on this tripod, and we'll use the Bunsen burner just to make sure it's a nice, fair test. So there we go. The blowtorch. So let's try setting light to strawberry-flavoured Angel Delight. Well, it's gone black. That's about it. In fact, if we dig underneath it and turn it over, you can see that the outside has gone black, but the inside is virtually untouched. You could scrape that out, add a little bit of milk. It'd be quite nice for a little afternoon or something or other. Might have the faint aroma of burnt toast, maybe. But this stuff is so good at absorbing heat, I don't know why they don't smear it on the outside of the space shuttle off a re-entry. But one of the things scientists do an awful lot of is analysing, especially anything that goes in the human body. So food gets analysed, and you get all these numbers on the backs of packets of stuff. One of the things they analyse for is the amount of energy. Now, this packet contains a little bit over 500,000 joules of energy. Now, that's a heck of a lot of energy. This stuff should burn pretty well, but it doesn't. It's mainly flour and sugar, and it should go, well, like rocket fuel, but... And the reason it doesn't is because it's a very, very fine powder, and it packs down. And so there's nowhere for the oxygen from the air to get in. So we've got a very similar problem than we had earlier. I have to say at this point, please do not try this at home. All right? Maybe, if we mix all this flour and sugar with the air before we try and set light to it, we might end up with something a little better. I said this is dangerous because I don't know how well it's going to go. And the reason for that is how the air moves it around in this room. So every time we do it, it's slightly different. But if we could have a 7, that'd be quite nice, if you don't mind. Yeah? Not a 10 today. There's some stage lights above me, and the guy at the back will get annoyed. All right? So 7. Here we go. Ooh, yeah, okay. Sure we can do better than that. That'll do. And you can see that perfectly ordinary stuff, if you know what you're doing, you can start getting chemical reactions out of it, like combustion, quite easily. In fact, there have been several industrial accidents where flour mills have exploded because of a little static electricity spark sets off the flour in the air. Please do not try that one at home. Because I only ever do this if the ceiling is far enough away. And that wasn't bad. That was about a 6 or a 7, that. B, can you imagine what's going to happen if the government finds out what you can do with something you can buy on a supermarket shelf? There's going to be HazChem warnings on the back of every packet of Angel Delight. Yeah? Even worse, the system in the supermarket is going to check that you don't buy too much, because you might want to do something naughty with it. So you're having a party, I don't know, and you're making this. This is quite good as a fake trifle. And somebody goes through and they go, bleep, 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 and the screen goes bright red and says, check, is this person a terrorist? Yeah. And your poor old next-door neighbour gets carted off by 2 burly people from security. Walk this way, please, we want to ask you some questions. Yeah? Let's not do that. Let's just keep it as a secret between you and me, what you can do with this stuff. Now, since I've discovered that perfectly ordinary stuff can be quite fun to play with, rather than, the bits and pieces out of the chemistry lab, I thought, well, what else can we use? So, cotton wool. So I've got a bit of cotton wool. Here we go. This is proper cotton wool, by the way. Some of the stuff in your bathroom cabinet has never been anywhere near a cotton plant. This is proper cotton from a cotton plant. It's dried plant material. There's lots of carbon and hydrogen in there. And there's lots of oxygen in the air. So if we get the two to react together, it burns. Pretty slowly. After all, here's the fuel. And we've got to wait for the oxygen from the air to randomly happen upon this, at which point it reacts with the carbon and the hydrogen in the cotton wool, and they produce heat and carbon dioxide and water, and that all disappears, and you've got to wait for the next bit of oxygen to come in. Meanwhile, the cotton wool's just sat there, and it's all pretty slow. Mind you, we've already speeded up the burning of charcoal, and you saw what happened when we speed up the burning of magnesium. Maybe we can do the same again. Now, the cotton wool is already in quite thin fibres, so there's quite a lot of surface area and not a lot of middle. The problem is getting enough oxygen to it all at once. Maybe we can solve that. I've got here some liquid oxygen. Now, this is oxygen that I've cooled down until it's so cold it becomes a liquid. And that means that, in this case, it's about a minus 180 degrees C, which is why I'm putting gloves on, because I don't want to get frostbite. So, let's take another piece of cotton wool. See how dangerous cotton wool is? I have to put a glove on. There we go. Oh, that's a bit too big. Hang on. Yes. There we go. Fluff that out a bit. In there. It's one way of proving how cold it is. So, now when I take this out, the liquid oxygen is going to start warming up and is going to become a gas. And that means it's going to run away from the cotton wool, and I don't want that. This is all round the wrong way. Who designed this? There we go, it goes right there. So when I take this out, I'm going to set light to it straight away. No messing about. Everybody ready? Have the lights down just a little bit, please. Here we go. Oh, doesn't want to come out now. Come on, you know you want to die. Here we go. And you can see ordinary cotton wool, if you've got enough oxygen there, ends up almost as an explosive. So, having discovered, the secret of this, of course, is the liquid oxygen, which means there's, seems to be snowing in here. This is the real secret, that because it's lots and lots of oxygen all compressed in together. Oh, like this. Must find some more stuff to play with liquid oxygen. So I went and talked to a friend of mine. He's the chief technician here. Now, I teach the theory of chemistry, but he does it every single day. He runs our laboratories. He makes sure that everything does what it should do. So I went to him and I said, liquid oxygen. I like this stuff. What else can we do? He said, would you like a biscuit? I said, be very kind. If I can have a cup of tea, please. Milk, no sugar. He said, no. Put a biscuit in liquid oxygen. So I've got a pack of digestive biscuits here. We'll avoid using the little tab because it never works. And in goes my digestive biscuit. That's better. No, stop floating. If any of you like dunking your biscuits in a mug of tea or coffee, you will know that one of the real problems of doing that is that when you get to the last mouthful of your drink, there's lots of bits of soggy biscuit in it, and it's like dredging a river, Don't get that problem here because the biscuit is instantly deep frozen, which is quite nice. So, sometimes you may well hear on the radio or the TV, some university has done extensive research. What on earth does that mean? It means doing an experiment, and you get a set of results, and then you say, okay, but just to check that those are the real results, and it's not due to, the way the wind's blowing or the temperature in the lab or something, you do it again. And you see whether or not you get the same results. And then you do it again, and then you do it again, until eventually you are certain that absolutely every time when you do whatever it is you're doing, you get exactly the same results. And then you change it slightly. And you do it all again. And you see the effect upon the results. Does it get faster, slower, prettier, green, whatever? Extensive research at the University of Plymouth involving a very large packet of biscuits and quite a lot of liquid oxygen. Some of the biscuits, by the way, were used for chemistry. Some were used for biology. Has revealed that we need that to soak for about a minute. I'm going to set light to that on this. This is a piece of steel gauze. This is steel wires woven together. This stuff is so strong that they use it as a safety shield for people who are learning fencing, with swords. My son-in-law actually fights broadswords. That's a really wide-bladed, heavy sword, and a sheet of that in front of him means that if the sword accidentally comes towards his face, he's safe. So a sword won't go through this. This is tough stuff. So I'm going to put that on there, and by now we should have a nice deep-frozen digestive biscuit. So, in there we go. Again, as soon as this comes out, it's going to warm up, and I don't want it to do that, so I'm going to set light to it very quickly. Here we go. Not bad. You can see it virtually ends up like a rocket motor. That is, in fact, exactly the same chemical reaction that happens when you eat a biscuit, only when you eat one, it doesn't do it quite so fast and quite so hot, fortunately. It's not... Oh. Seem to have made some charcoal. Maybe I could make some gunpowder. Put that out. The important thing I want you to see, though, is that we've managed to melt holes in the steel gauze. Now, I should warn you at this point, if you go and tell some of your friends that you saw somebody melt steel with a biscuit, they're probably not going to believe you. But if you know your chemistry, you can melt steel with an ordinary biscuit. Okay, well, that's not bad. So, at which point, I think it's time for the last experiment. Whereas these experiments, you've seen them, and almost that's it. This one, we already have a video up on YouTube, and you can watch it. You need to put in the magic words Jelly Baby and Plymouth, because we are going to torture an innocent little baby. Now, these babies come in different colours. We've got an orange one, a black one, a yellow one. Oh, here we go. A red one. Oh, a green one. No, I think we're there. I think that's all we got. Now, I'm going to leave the lights up on the audience for this point, because you're going to choose which of those innocent little babies goes into my torture chamber. Now, before I do, though, what I really need at this point is a glamorous assistant, but I haven't got one. So, Mike, can you come and give us a hand, please? You will, of course, need a pair of safety specs.
Of course.
All of a sudden, I'm regretting choosing him, but never mind. If you could just melt that. If it starts boiling and smoking, you've got it over hot. Okay? I have to say, whenever I've done this in schools, I've usually got the head of chemistry to do this, and they overcook it. Okay? Usually when I get somebody who thinks they don't know what they're doing, they do it perfectly. So just don't break the sequence. So we've got a black one, a red one, an orange one, a yellow one, and a green one, and you're going to choose which of these jelly babies goes into my torture chamber. Okay? And when we're going to do this, you've all got one vote. And when I call out the colour, if you think that colour should go in the tube, then you put your hand up. Okay? So, how many people think the orange one should go in the test tube? 3. 3? You are the weakest link. Goodbye. The yellow one. I'm sorry, you're not the weakest link. The yellow one is. The green one. Oh, hello, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's a bit smoky in here. 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I see your hand, 22. It could be you. The red one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No. The black one. Oh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. No. By quite a wide margin. It's the green one. How are we doing? Do you do plumbing at home? No. Teamwork. Now, give it a good roasting. Yeah, that's it. That last bit will go. All right, thank you. Big hand for my glamorous assistant, please. Right, at which point, there's only really one more question I need to ask. Head first or feet first? Ooh. Head first or feet first? Yeah, it always is. Here we go. We do have larger tubes for students that don't do their coursework. At which point we produce lots of evil-smelling smoke. It's got to be chemistry. Thank you very much indeed.